In this video, we're going to explore how to find the approximate area under a curve. There are two main techniques to help us out with this, and they both rely on geometry. The first is to approximate using rectangles, and the second is to approximate using trapezoids. Let's get into it. The area under a curve is defined as the area bound by the curve and the x-axis. For example, the area bound under this curve is the shaded area. The curve and the x-axis form the perimeter of the shape. The problem is there's no generic formula for the area of this kind of shape. It's completely unique. But we do have a method to approximate the area. For example, the area of a rectangle is given by its length multiplied by its width. If we were to replace the entire shape with a rectangle that has the same width and length as this shape, then we could at least get an approximate area, but we can do a bit better than that. Instead of replacing the shape with only one rectangle, we can replace it with a series of rectangles back to back. Notice how using more rectangles has reduced the amount of excess area of the shape. The more rectangles we use, the better our approximation is going to be. So, here's how it works in math methods. You start by figuring out what the width of each rectangle is going to be. In this case, the question has already told us what the width is going to be. It's just going to be pi on 6. Next, there's actually two possibilities when it comes to aligning these rectangles. You can either align with the left endpoint, in which you take the left-hand corner of each triangle and align it up against the curve, or you could do the exact same thing with the right-hand side. This question uses the right. Depending on which method you use, you'll actually get a different result, and that's why it's important to figure out what the question is using. Okay, now we know the width of each rectangle, but in order to calculate the area of each rectangle, we need to also know its height. And since each rectangle starts at y equals 0, the height of each rectangle must therefore be the y value of the curve, since it intersects the curve at that endpoint. Therefore, the height of each rectangle can always be found by subbing in the corresponding x-coordinate back into f of x, although sometimes the question is nice to you and it lets you read it off the graph, like in this case. Now that we know the height of each rectangle, we have all the information we need to calculate the total area. We just need to find the area of each individual rectangle and then add them all together. Remember, the width of each rectangle is still pi on 6. Even though all the x-coordinates increase over time, we're only interested in the gap between each rectangle. Trapezoidal approximation is more accurate, but it's also a bit more difficult. Instead of using rectangles, which is just length times width, we use trapezoids, which have a much more complicated area equation. The main difference being that instead of just aligning one endpoint to the curve, we've got to align two now. And just like before, we need to figure out what the width of each trapezoid is going to be. But in this case, we have to calculate it. The interval is going to be from -1 to +1, and since we need to fit 4 trapezoids in that interval, that means the width of each trapezoid must therefore be a half. The good news is the endpoints have already been aligned for us, so we can skip step 2 and move straight on to step 3, which is to figure out the y-coordinates, or the height, of each trapezoid. Just like before, we can find the height of each point by subbing in the corresponding x-coordinate back into f of x. At this point, we have all the information we need to figure out the total area. We just need to find the area of each trapezoid and then sum the results together. The area of a trapezoid is given by this equation, so all we have to do is sub in the width and the height values of each trapezoid. As a final note, your exam reference sheet will actually write this equation out just a little bit differently. Here's where that comes from. The area of a trapezoid is given by h multiplied by a plus b all divided by 2, where a and b are the different lengths of the trapezoid. If we are interested in adding 4 trapezoids together, then the equation would look like this. We can then take out the common factor of h as well as that divide by 2. Here's an interesting point. Notice how each trapezoid shares a point with the previous trapezoid? This means that all of the b terms are actually a terms of the next trapezoid in line. So instead of writing a and b in the sequence, you can replace all those b terms with equivalent a terms. Better yet, not only can we replace the b terms with a terms, we can also replace the a terms with f of x terms, since all those are just points along the graph at specific x values. Now all we have to do is rewrite the h term. The h term is the width of each trapezoid, and if you recall from earlier, we found the width of each trapezoid by defining the entire interval and then dividing through by the number of trapezoids in that interval. The length of the interval is just the last x value subtracted from the first, and the number of trapezoids that we're going to divide by, let's just call that n. All that to say, either approach works. You can use the thing in the formula sheet if you want to just quickly smash it all out, or if you prefer to think geometrically, then you can think in terms of each individual shape and then adding them all together. Either approach works. You're not going to be marked down on the exam if you don't use the thing in the formula sheet. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll send you to my website.